Okay, let's get started. Good morning. Today's lecture uh, is about applications of compactness. And specifically, I want to talk about something that I mentioned in this motivation for this week, which is principal component analysis. And one step in computing these so-called principal components is finding eigenvalues. And if there is time, we might discuss other things, but these are the main things. Also, for those who came now, feel free to ask anything about the exam or any logistics in the chat. I'll get to them now or later. I made some announcements already on Campus Wire. So we have a midterm on Friday. There will be no videos for that. There's no homework due this week. That's the basic things. Okay. So an outline, we'll spend some time on discussing what is the motivation to convince us that these concepts are actually interesting. Then I will state a theorem. It's a slightly modified version of actually what I put in the week 3 plan, because both of them are true, but this turns out to be easier to prove. And then we do the proof with focusing on the steps and going through them carefully. And then if there's time, we'll move on to some other things, but mostly those will be on Wednesday. I don't think we will have much time. There's a question in the chat: what hours will the exam be open? The exam will be open Friday, midnight, between Thursday and Friday, until Saturday at 12. So you have all of Friday to do that, including if you need some time on Saturday. So it extends until Saturday. Yeah. And any other questions, feel free to post there. There will also be more information. I'll post it on Campus Wire and make it clear later. So, data analysis, what is it about? It's about finding patterns in data, making predictions, or simplifying data in various ways. Now, a standard example of that is linear regression. And way to understand that is that we have some sequence of data points, xi, yi, say in the plane, x and y coordinates. Now, there's always some measurement error, or you could think that it's some error in the model, that there are some factors that haven't been accounted for. But so these data points are perceived to roughly to be modeled by some lower dimensional model, or in this case, a linear model, up to some sort of error in the system. And the question is coming up with the parameters, in this case, the slope of this line, or the so-called the best linear fit. And this is the idea of a low dimensional representation. If we took all the data, all the endpoints xi, yi, then this would be a very high dimensional data, thinking of them all forming a matrix with 2 columns, xi and yi. But reducing to this linear model reduces essentially to 2 parameters, especially if we're passing through the origin, only 1 parameter. Now, not all lines or not all models pass through the origin, and there's often a normalization that's assumed, is that one subtracts a constant so that the average of the data of interest is 0, and that the variance, sometimes it's normalized so that the variance is 1, but in this, we have to assume that all the data, so the x measurements and the y measurements, have been normalized so that they have average 0. This corresponds with this geometric fact that the line is passing through the point. Now, okay, this is not a data analysis class, but the way to think about it and to connect it to this class is that finding a best fit is like an optimization problem. It's one where we find model parameters that minimize error in the predictions. So any kind of low dimensional representation should have a corresponding optimization problem. Whenever we have an optimization problem, one of the main questions is, does a minimum exist? And if that minimum exists, is it, what can we say about it? How can we compute it? So examples of this are rampant all over the place. I don't think I need to justify these too much for you to believe that such low dimensional representations would be important. Any kind of modeling application, we want to find model parameters. It's an example of such a model. Sometimes they're nonlinear models. I will focus on linear models in this lecture, and very simple ones actually. But there are other applications, for example, finance. We might want to understand financial data. We want to say, maybe I'll mention one simple calculation that I did. It wasn't very good necessarily, but if you have a portfolio, you might want to classify or group the stocks in groups where each group is highly correlated with each other, but the groups are not correlated between each other. So in other words, you might want to find the factors that are influencing the changes in your portfolio. Now here you have a huge amount of data that is prices of the individual stocks or components of those stocks, and you want to analyze that, make some sort of linear fits into this. Other applications are image processing. Now images are inherently very high dimensional objects, so if you want to run many algorithms on them, they will run into problems, because if you have thousands upon thousands of images or tens of thousands of images, each of them, say resolution 1,000 by 1,000, then you have a very high dimensional space. And even if with efficient linear algebra, it may be infeasible to do in a practical amount of time. Say k-means clustering or many of the common clustering algorithms, they are nearly linear but not close enough, or they might be superlinear algorithms. And in practice, it's not feasible to operate on data sets of that size. So one technique that is common and that at least shaves off a factor of the running times, and therefore can be practically a difference between a few minutes and a fraction of a minute, which is practically significant, is dimension reduction, reducing the size of the data into some low dimensional model. And that's the kind of low dimensional representations that I'm interested in this lecture. And in, say, in 3 dimensions, you could have data, and then you're looking for some sort of plane that fits into that data. And that's your low dimensional representation that you're looking for. Okay, so what's the scheme here is we have our data, we construct a low dimensional representation, and the tools to do that are finding eigenvalues and eigenvectors. These are the standard tools in principal component analysis. I won't justify why these are natural, but these are the tools. Specifically, these eigenvalues vaguely correspond to significance, and in case it's been a while of your linear algebra, don't worry, I'll remind you what eigenvalues and eigenvectors are. But in terms of translating these between these concepts, eigenvalues should be thought of as numbers measuring significance of a feature. Eigenvectors should be sort of the independent directions or features of the data. This is one way of understanding it. And these lead to this so-called principal component analysis method, PCA, principal component analysis. Okay, so what does this look like in practice? And we're getting a little bit closer to the scenario of this theorem statement. So you connect actually this practice with this mathematical theory. Before I say this, there's a question: does significance mean weight? So I have to say I'm not sure of the technical meaning of the word weight, specifically in data analysis, but I would assume that these are very closely related, if not exactly the same. So so significance, by that I mean here the percentage of the total variance that this particular feature explains. So in this picture, say, this eigenvector corresponding to this feature, this linear feature, would have a very high significance, whereas these components that would explain this variance would have a relatively low significance, therefore a low weight. So I assume these are related. They're not quite, not necessarily equivalent, as I'm not fully an expert in this area. Okay, so what we have a matrix of data. These consist of some measurements here, columns, data 1, data 2, data 3, etc. Each consisting of possibly many measurements. So this could be the prices of stock 1 on different dates, price of stock 2 on different dates. And again, there's some usually normalization process to make these vectors have comparable variance, and also to ensure that these linear approximations pass through the origin. It simplifies these calculations. Now, again, focusing on how do we reduce it to this theorem statement. We are trying to find features in this data, and how principal component analysis works. It constructs a certain matrix A by taking Z transpose. This is sometimes called the covariance matrix. What it's measuring is the interdependence on the data. And then, but one of the benefits of this covariance matrix is that it's symmetric. And I'll define also what this is. So this always has a full set of eigenvalues, sigma 1 through sigma n, and corresponding eigenvectors. And what principal component analysis does is that it takes the largest of these eigenvalues and takes the corresponding eigenvectors of unit length. And these features somehow are capturing the main directions in which the data is pointing. Now, if we want to say reduce data, then what we can do is we can take our data and we can project it onto this data by applying a certain matrix on the left. The way I chose columns and rows, in this case, it would be applying on the left. So out of this comes data that is, instead of being p-dimensional, it will now be k-dimensional. And then you can analyze this data and do other methods on it. Depending on your applications, the interpretations vary a little bit. So I did a very simple, and I said this already, I'm not an expert in this, so I'm not doing things that probably are practically reasonable, but I just did a very simple application of this that I thought would be interesting. At least I was curious to see what would happen. So what I did was, we all know that the stock market has changed a lot in the past 4 months. It has gone a lot down around mid-March and then somewhat back up. And different companies have been grossly differently affected. So airline companies have collapsed. Some healthcare companies have either risen or stayed neutral. A lot of other companies have decreased, but not as seriously as, say, airline companies have been hit. So what I did was I took stock market data, closing prices, for about 45 different companies, just companies that I could think of. There were 10 airline companies, there were a number of banks, there was Lyft, Uber, Tesla, Google, Apple, etc. And what I did was I took, to estimate sort of the data that would capture this drop, and it's maybe not ideal, it was a very quickly done test, just to show how this can be used, is I took 15 days in January, 15 days in April, constructed the data, normalized it, and looked at the 2 main principal components, so 2 largest eigenvalues of this covariance matrix. And then I projected the data onto that. So this is the data points as projected onto a 2-dimensional subspace. And this data that's really 30-dimensional, and it included 45 data points, so not very huge in some ways, but actually 97% of its variance was about something around there, 90% of its variance was explained by these two largest eigenvalues. So they're capturing something real from the data. In this case, what one can see, it's not as clear as I would have maybe hoped, and which is maybe a little bit surprising. You can see certain groupings forming, corresponding, and this is why it's actually this kind of visualization is used for clustering, is that, say, if you look at this red group here, these are all airlines. You have Azul, you have Spirit, United Airlines, Delta Airlines is there, Alaska Airline Group is there. So those are all airlines. Now, there are some outliers. Zoom stock has skyrocketed. It's kind of in an uncomparable way to many other stocks. And then there are some weird ones, like Tesla has behaved weirdly, Amazon. So these form a sort of cluster of groups of people who it's not as clearly identified, but risers. And then there are some other much harder to recognize clusters that don't seem as compelling. In this cluster, you have a lot of banks. There's American, there is Capital One, there is Chase, Wells Fargo. There's also Uber and Lyft are in this group. And then there's another cluster that seems to contain a lot of the tech companies. So Apple, Google, Microsoft are all contained in that group. These boundaries are not very well defined, but this is just to give you a sense of sort of what can this method be used and why would you care. So lessons of this example is that, okay, principal component analysis and data analysis leads to optimization problems because they connect to eigenvalues. And two is that these have a real practical significance in, say, grouping data and extracting features of data that you find interesting for your applications. Okay, so very interesting practically, but mathematically, so we're a theoretical class, we're not a practical class. Why would you care about these questions, or what is the theory side of these questions, is that why does a best fit exist? We are looking at optimization problems in high dimensions, and there's no reason for these minima to exist. And then the second question, really outside of the scope of this class, is how to approach those minimizers. But the first step is, well, whether that minimum exists, because any method that would approach it would have to approach something real. So we should prove that a minimizer exists. And the tool to find these models, as discussed, is eigenvalues. So now we'll do a bit of a review of linear algebra. This is a transition away from this motivation picture. Now, a bit of linear algebra. We have a matrix A that is this time an n by n matrix. So A11, ANN, A1n. All the way up to AN1 and then ANN. So an n by n array. This array, it can operate on vectors by the usual multiplication. Let me know if you don't remember how that multiplication works. Okay, it's operating on vectors in Rn. So there we have a norm, the norm that we have already seen, which is the square root of the sum of the squares of the components. And corresponding to this norm, we have a distance, the normal D2 distance that you've seen in the homework and in some of the lectures, the norm of the difference between x and y. Okay, so this is our setting, this is our metric space. So this translates this general applied problem of finding a model or model parameters into language that we understand in this class. So the context is really working on metric spaces and functions on those metric spaces. And the object that we are, turns out that we are looking for is an eigenvalue, and we define a vector as being an eigenvector with corresponding eigenvalue lambda if A times V is equal to lambda times V. So maybe this is a good point to just remind briefly, how does the multiplication work? If we have the first column is A12, A2, A1, A11, A12, A13, and then some more entries. So this is a 3 by 3 matrix. And if it operates on x1, x2, x3, then the first component, the product, would be always computed rows times columns. So there would be first row, second row, third row, but let's just compute the first row. That would be given by A11 times x1 plus A12 x2 plus A13 x3. A11 x1, A12 x2, A13 x3, and then the other would be similar. So the way to memorize this, as you've probably seen, is the components of AX I are, you take the ith row of A times the jth entry, and you sum up over the jth entries. So AIJXJ. Now in Rn, and for this analysis, we also need to look at the inner product. That's needed for the proofs, is that the inner product is the familiar xi, yi. This was also mentioned in one of the lectures. Okay. So, okay, we have our matrix. Its elements are listed by Aij. The matrix is called symmetric if its transpose is equal to itself. And that, what is the transpose? The transpose is where we flip the components. We flip the matrix across its diagonal. So Aij entry is flipped to Aji. And if these two arrays are the same, what it really means is that Aij is equal to Aji. Now in practice, what this means and how you use it, the basic lemma, is that if A is symmetric, then inner product of AX with Y is the same thing as inner product of X with AY. And this is actually an if and only if, so it goes both ways. Sometimes this is used as the definition of being a symmetric matrix. And the proof is fairly simple. If you expand this sum, it becomes a double sum of I and j, Aij, xi, yj. And if you sum up on the other side, it becomes a double sum over I and j, but this time the components are just slightly different. Xi has the same index, yj has the same index, but this time the operator, the A is multiplying y, so it's paired with, and that should be Aij there. No, sorry. Here I had it wrong. On that side it was wrong. It shouldn't be automatically the same. So the outcome of AX is this sum, AJI, XI, and it's paired with YJ. And now the output on the other side is the opposite when it's acting on Y. But because the index Aij is equal to AJI, you get the same answer. The terms are the same. Okay. So we have these matrices, they're acting on the space. Okay. Now let's try to connect a little bit these two classes to each other. So if A is an n by n matrix, we get a map from X is sent to AX, and this is a mapping, lambda X. So lambda X is equal to AX. It's a linear transformation from Rn to Rn. Now this mapping is continuous. Continuous in the sense of our class. We haven't yet stated what we want to state about optimization, but because we will need to talk about continuity, this is a good intermediate step before we get there. So, okay, this mapping is continuous. What it requires is that we have to show the definition of continuity, that for every epsilon positive, there exists a delta positive, so that if the distance on the domain side is less than delta, then the distance on the image side is less than epsilon. And this should hold for every x in this space as well. Every x in Rn. It turns out that this x in Rn doesn't matter. The choice won't matter. This terms that we will introduce later is that this function will be uniformly continuous. So we won't have to fix that first. So, okay. To write the proof in that generality, let's just first fix an epsilon positive. And we do that because we want to make sense of the right-hand side. And now we have to say, well, that's for every part, we have to say that there exists a delta. So we have to think about the estimate, that's step 2. Find the delta that works, and then prove that it actually works. So side computation, let's think a little. Okay, so we have distance is what we want to estimate. So let's look at distance between AX and AY. This is the same thing as norm of AX minus AY. And this is the same thing as norm of A of X minus Y by linearity. And this is the same thing as square root sum of, we take the sum over the components, Aij xj minus yj, a little more space there. All this is the ith component, that's squared, and then summing, sorry, this inner sum is over j, and the outer sum is over I. So summing j over j equals 1 and I equals 1 to n, because this is the ith component of A, ax y minus y, and then we take the norm of that with the square on the inside. Okay, so we have this expression. This is the distance between ax and ay. Now, how do we estimate this from above? A is a fixed matrix. There's a simple trick that is the stupidest thing you ever do, but since A is a constant, let's use that in a basic way. So A is a constant, so all of its components are constant. So we can define a quantity. Let's call this the infinity norm of A. Is the maximum of the absolute values of all of its components. And the reason for this is that, well, we want to estimate each of these components from above by its maximum. So let's see what we get from this. This is bounded from above by sum I equals 1 through n, sum j equals 1 through n, and there's parentheses, A infinity norm squared times xj minus yj squared, 1/2. Okay, now we want to get the distance in here. So let's recall the homework. So we had that xj minus yj is always less than the distance between x and y. So what we then get is sum over I equals 1 through n, sum over j equals 1 through n, the norm of a squared times the distance. Actually, we don't have this, the square shouldn't be there yet. It will soon be there. Squared 1/2. But now we're summing over a constant. There is no I or j in here. So what is this? This is the number of terms, n squared. So, well, we have to be a little careful. So the inner sum is n squared times the square of this. And then we get another n. So we get n cubed times the norm of a squared times the distance between the points squared 1/2. That's just the sum, estimated term by term with the constants. And then when we get what we want essentially, because this here is n to the 3/2 constant times a norm constant times distance between the pair of points. And you get a bound and you think, can I make this small by ensuring that x and y are close? Well, yes, because I can choose the x delta so that we absorb this constant. So we want to make this less than epsilon. So we have to pick a delta here. So we pick a delta equal to epsilon divided by that factor over divided by a infinity norm times n to the 3/2. And then we can take away the think and this proof works. Initially it was irregular, but this estimate actually turns out that gives us exactly what we need. Any questions on this? Okay, so linear maps are continuous. Okay, so now we get to state our theorem. So principal component analysis requires computing eigenvalues. How do you find eigenvalues? How do you prove that they exist? Well, as a crucial step of many of such proofs, one has to prove that if you have a symmetric matrix, then the matrix A has at least one eigenvalue lambda and a corresponding eigenvector V, and that these can be found by a maximization part. So the eigenvalue lambda can be defined as a supremum over all unit vectors x of inner product of ax with x. So this is a little different from what I wrote in the motivation. It turns out that the proof is considerably easier with this, so that's why that's there. And well, the theorem says more than this. Okay, so the eigenvalue is this, but how do you find this V? This V is the one that maximizes this expression. So there is a V with norm equal 1, such that this side should be a little corrected, so that AV in a product with V is equal to this supremum that we hope. So we don't know that there is a maximizing one. That's why we have to put a supremum there. This V satisfies moreover this eigenvector equation. So they form an eigenvalue-eigenvector pair. This is far from, still after this one would have to do more work for principal component analysis to work, but this is a basic fact that leads to that. There are many proofs of this. You might have seen some other proof in another class, but it turns out that thinking of this as an optimization problem is actually very useful. This kind it's a maximization problem, even though our original problem is minimization. So you could think that you're maximizing the amount of information of the data that you're capturing. This leads to algorithms. So I mentioned in the motivation that there's this power iteration method that's basically based on the observation that this can be seen as a maximization problem. Okay, so we want to prove a maximum is attained. So if we want to prove this, I mean, this class is all about proofs, is we have to prove that we can use extreme value theorem. We want to use extreme value theorem. Of course, that's not quite enough. There's all these claims about connecting it to the linear algebra that we have to get to after that. But the first step is actually proving that there's something that we can talk about that maximizes this function. So to do that, we have to look at two things. We have to look at the set of constraints, or the set where we are optimizing over. And we have to look at the function that we are optimizing. And the set we are optimizing for, what do we need for that? If we want to prove easily that the maximum exists, well, the easiest condition, or the one that we have to at least have to worry the least, is to say that the set is compact. Well, okay, let's go through this. Why is it compact? Well, to show that it's a subset of Rn, so we have to show that it's closed and bounded. And okay, each we have to check and argue why it's true. Well, S, if we define the function g of x equals the norm of x2, then this is the same thing as distance at x to 0, the 2 distance. This is continuous. We have shown before that the distance to a point is continuous. Distance to 0 is also continuous. So S, which is the pre-image of 1, of the singleton 1, is also closed, because the singleton 1 is closed. A singleton is always closed. By theorem. We had a theorem to this amount. You'd have to quote, if you use this fact, say in an exam, you should quote the theorem that you used. Okay, so the set is closed, but it also needs to be bounded. A unbounded set could lead to problems. So this set is, well, it's the unit sphere, points at unit distance from the origin, so everything is contained, say, in distance 2. So let's pick, say, r is equal to 2, then S is equal to the points whose distance to 0, to the origin, is equal to 1. Well, each of those distances is less than 2, so it's contained in all those x's such that distance x to 0 is strictly less than 2, and this is the unit ball of radius 2. So S is bounded, by the definition of being bounded. That is, that there exists an R such that you're contained in the R ball. So bounded by definition.
Okay. Could you scroll up for 1 second? Just to see the definition of S again.
Yes. So S is all those points whose distance is equal to 1.
Thank you.
So geometrically, it is the set unit ball or its higher dimensional analog. Nothing inside, although it doesn't matter for this argument. So the set is closed and bounded, again, by theorem. So by Heine-Borel, S is compact. We're done. So the set is compact, so we have a good domain to optimize over. But if we want to apply extreme value theorem, we need that the function we're using is continuous. And okay, you could do a direct calculation. I don't want to go over it now because I'll just leave. You can look at these notes. It almost completes it. But there's a much better way to see this continuity using by what we said earlier and some tools that we will discuss Wednesday, is that you can decompose this function into pieces that are easier to understand as continuous. I mean, you could express this even easier, that this is a polynomial expression actually, and therefore it's continuous. But if one wants to open up that a little bit, you can express it as a composition of two things. First, one function that sends x to a pair of x and ax. So what is this an element? X is an element of Rn, and ax is an element of Rn. So the pair of them is an element of Rn cross Rn. But what does the function do first? It sort of replicates x into x and ax. And then another function, what it does, it takes in two vectors, x and y, and computes their inner product. Now this function f can be thought of as a composition. First you send x here, and then you send x with c. So b and then c. And if you plug these in, so plug the b into the function c, then you exactly get the definition of f. And compositions of continuous functions are continuous. Therefore, this function is also continuous. So this requires showing that c is continuous and b is continuous. But b's continuity is essentially what we showed earlier, although in this is a slightly different form. Okay, so we'll discuss this more. And later, and one of the main issues here is that what do we mean by Rn cross Rn? So there is a simple answer at this point. Well, this is the same thing as R2n. Or there's the answer that we will give on Wednesday, is that of a product metric. So it's a way of making sense of pairs of objects and defining a metric there. Great. But okay, now we have a continuous function on a compact space. The continuity, we did not explain everything, but at least mostly. We want to then apply extreme value theorem. So S is compact and F is continuous. So there exists a V equals V max, so that in S, with F of V is equal to supremum of V in S of F of V, or F of X if we want to use a different variable. So the maximum is attained. Okay. Define V as this F. But we don't know yet that this, so we know that there is this V, and any procedure that leads to this maximum will give this V. So this is the idea behind, say, power iteration, is that converges to such a V. What we don't know yet is that it's an eigenvector. And we haven't defined what lambda is. So this is what this last step is doing. So we have to show that this is an eigenvector. And this is technical, but it's the last thing from this lecture. So let's go over it roughly what's involved. So, okay, we choose V so that it's the maximizer of this expression. And what we want to show is that AB is parallel to V. Want to show this? I mean, this is the same thing as saying that there exists a lambda such that AB is equal to lambda V. Being parallel means being a multiple. I mean, this is old stuff. Okay, suppose not. Let's argue by contradiction that it wasn't parallel. Well, then what you could do is you could take AB would point not in the same direction of V. So you can subtract the direction of V to find some part that is perpendicular. And this is what this W perp is. And by construction, this perp will be perpendicular to V. Now, what the idea is that, if you remember, we have this unit sphere S. We have our V. And the idea is that we will move a little bit in the direction of W perp. And the function will decrease in that direction. Or, well, we'll get a big contradiction that it can't decrease in that direction. So this is in a sense, there will be a cleaner way of doing this with Lagrange multipliers, but I don't want to now discuss them at all. So what do? Well, we go a little bit in the direction of V perp. This will no longer be in the set S, so we normalize. We divide by its length to get a point in S. And then we look at the function at this new normalized point, h of t. And this is a common thing in optimization, and what I want you to take out of this. We may get back to this at a later point in the class. Certainly you'll see this in optimization a lot. Well, what do we know about this function? H of 0 is equal to AB inner product with V. Okay. H of t is a WT inner product with WT hat, which is another point in S. So because V is a maximizer, these points are always less than or equal to 0, H of 0. Now, if you look at all these expressions, AB hat, VT hat, inner product with WT hat. This function is actually continuous, that you can show. You expand all these expressions, say. It's also differentiable as a composition of differentiable things. So this is a single variable function, so it's all contained in 131a. We don't have to talk about multivariable differentiability. But now we know by single variable extreme value theorem that this function, it's differentiable and it has a maximum at 0 because every other value is less than that. Therefore, the derivative at 0 is equal to 0. Now you compute this derivative, and what you get by quotient rule is AB inner product with W hat perp. And then you get a second term when you differentiate the denominator. But fortunately, by this perpendicular property here, we get that second term is actually 0. So this uses star above. A simple basic exercise to do. But we don't now have time to discuss this. And that's not crucial. It's not. I don't care if you know how to do this calculation. It's about the process. So what we get is that this is still equal to 0. And we're basically done because what is left is the denominator is 1. We have a factor of 2. And AB inner product with W perp. So we get that the inner product of this with its W perp is 0. So AB is perpendicular to W perp. but AB is the sum of a parallel part to B and a perpendicular part to B. And if you take the inner product of that with W perp, what you're left with is just the perpendicular part, because the inner product of this with the perpendicular is 0. This is equal to the perpendicular part, and ultimately we get to the norm of WT is 0, but the only way for the norm of the WT to be 0 is if the vector actually were 0, which is a contradiction. Since WT should not be equal to 0. And with that, we are able to conclude our proof that, okay, so AB has to be parallel to V. So there exists some lambda such that AB is equal to lambda V. And now if you take inner products, and this is where I end, apologies for going a little bit over time. Now AB is equal to lambda V. So this is lambda V inner product with V, but V is a unit vector. So V inner product with V is 1, and we're left with 1 lambda. So we're done. That's the end of the proof. So this was a lot of work, but very well. I hope you found the motivation appealing, and you were able to see how we use these closed open continuity, how we prove these continuity properties, and how it all came together in a very real application that, say, if you take optimization, you might see. So these notes will be online. If you have any questions, feel free to ask. I'll stick around for a few minutes. But this is the end of today's lecture. Yes. So there's a question in the chat about what HT is. So I'll expand that a little bit. So first, graphically, okay, let's draw it a little bit more carefully. So we have our sphere. We have our V, which is the maximizer of the function. And then what we're doing is we're going in a perpendicular direction. So W perp is that direction. We're taking this vector, but this is WT. And then we're normalizing that vector so that it lies on the sphere. So this is WT hat. And as t varies, we trace this curve on the sphere. And what we're doing is h of t is equal to f of WT hat, which was equal to a of WT hat, WT hat. So as t varies, this point varies on the sphere. It gives a different point to plug into the function and gives us this function. And at 0, so h of 0 is f of W0 hat, but W0 hat corresponds to when we add nothing to V. So this is just WV divided by norm of V, which is 1. So f of V, which is AV V. And this was the maximizing among all of them. So h of t is always less than or equal to h of 0, because this was the maximum. Did that clarify, David? Do you have more? Yeah. Good. Other questions? I know this last step was quite technical, but it's the one where we have to use some linear algebra to connect these concepts. But what you can take out of this is that even if you don't follow the calculation, is that often what helps in studying optimization problems is by considering some sort of variations. So we start from our optimum solution, or what we think is optimal, and we move it around a little bit. But moving it around too naively, say if I took this point and I moved it in this direction, it would take it outside of the constraints. We're optimizing on the unit sphere, so we cannot move the point outside of it. So whenever you do that, you have to somehow project back onto the space. And this is this normalization that we're doing here. This way, what we get is a way of varying points along the sphere. So what we're really getting is a curve along our constraint set. A lot of these concepts, they go further into optimization than we would really like, but all we need here is that these are points on the sphere. This is the function at those points. So because 0 is the maximum, that's where h of t is less than or equal to that. You differentiate, you see what equation you get from that. And it turns out that means that actually AB has to be perpendicular to B, is the equation that we get. Of course, initially assuming that you actually weren't perpendicular, which is the source of the contradiction. So, good question. Let's add that. So WT hat is defined as WT divided by norm of WT. So WT hat's norm, if you compute it, using some properties here, is the norm of WT. This is a scalar, so it goes out. Norm of WT divided by norm of WT, which is 1. So this is, how do you make a vector into a unit vector? Well, you divide by its length. So what we're doing here is actually dividing by its length. And the set S consists of all the elements X such that norm of X is equal to 1. Well, WT hat has norm equal to 1. Therefore, it's a member of S. Another short question. Okay, so if not, feel free to ask on Campus Wire or other. We will continue on Wednesday more along, say, product spaces and continuity of functions, more familiar topics, but hope you found this interesting. Until next time.